Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn about convolutional neural networks in PyTorch. CNNs are a type of deep neural network that is most powerful in image processing tasks, such as sorting images into groups. And CNNs consist of layers that process visual information. So a CNN first takes in an input image and then passes it through these layers. And there are a few different types of layers, and we will start by learning about the most commonly used layers. And these are convolutional layers, pooling layers, and fully connected layers. So let's go ahead and start with the convolutional layers, which is here the first layer here in the network. So the first layer here processes the input image directly. Now, in practice here, this would be typically a grayscale image, but you can also do a color image. So this layer, the convolutional layer, takes in the image as input, and then, as its name suggests, it is made out of convolution kernels or convolutional filters, which we learned about in the previous lesson called convolution kernels in computer vision. So each of these filters extracts a specific kind of feature. So for example, you can detect the edges of an object. And the output of a given convolutional layer is a set of feature maps, or also called activation maps, which are filtered versions of an original image. Now, why are they called activation maps? Because you do convolution, so you apply those filters to detect visual features, and also you apply a ReLU, for example, an activation function, and they are typically placed after a convolutional layer to slightly transform the output so that it's more efficient to perform backpropagation and effectively train the network, right? Because you're handling the problem of the vanishing gradient problem. And also when you're visualizing your data, once you visualize a transform and an activated filter, you can see more clearly the edges and the specific features that it detected. So this is how we do it. So that's the convolutional layer. And then after some convolutional layers, what you do is you have the next one is a pooling layer. And in this case, we call it max pooling. And these layers take in an image, usually a filtered image here after going through convolution, and output a reduced version of that image. So these pooling layers reduce the dimensionality of an input. And so why would we want to do this? Suppose we're not doing max pooling, we don't reduce the dimensionality of the image, we're going to have a lot of weights, a lot of parameters, because remember, what connects a layer to the next are a set of weights and a bias. So the model parameters, and we have so many parameters. The more parameters we have like this, the higher the chance of overfitting and over training the network on the specific training data so that it won't generalize well. So we'll be decreasing the dimensionality of the input. And so these max pooling layers look at areas in an input image. Let's say, for example, a 4x4 pixel area, and choose to keep the maximum pixel value in that area in a new reduced sized area. So and max pooling is the most common type of pooling layer in CNNs, but there are other types such as average pooling. So for example, given for example a 4x4 pixel area, it will convert it depending on how you set up the max pooling. Let's say you're decreasing that dimensionality in half, then you would grab for every 2x2. Let's say you set a parameter to 2x2 window here for your max pool filter. You would grab the pixel value that has a maximum value in there. So what you're doing is you're grabbing this filter image and just making a smaller version, reducing it, grabbing the areas that have the highest value, so the highest intensity values. And this is also nice because as you decrease the dimensionality of the input, as you downsample these images, the filters are able to cover. So you have the same filters, let's say, and you're able to cover a larger area in that downsampled image. So you're able to detect larger features. So for example, in this case, you might have these filters that are going across the image and detecting, let's say, a little edge here and there and so on. If you apply those convolutional filters in a later layer, in a downsample layer, because let's say the size is the same, you'll be able to detect a much bigger area and detect just bigger features and so on. So that's how, as you go through deeper into the network, you're able to detect all of these different visual features. So convolution plus ReLU, so extract output activation maps or feature maps, and then max pooling will just keep the highest intensity values in a given window that you pick. And then here, we're coming to the last layers here, which we call them the fully connected layers. And their job is to connect the input they see to a desired form of output. So this typically means converting a matrix of image features or feature maps into a feature vector. So we're flattening it. So we're making these matrices into a vector, and the dimensions in this case typically would be 1 times let's say the number of classes. Suppose you want to classify objects and you have 10 different different classes. Let's say object 1, object 2, object 3. Then you want the output to be a feature vector with 10 values, 10 number of classes. And here the last one, the softmax, is in the case of classification of an object, we want to output the probability for each one of those classes. Let's say if the network is fully trained, it's going to say, oh, 99% probability for class 3. And for all the others, the probability will be very close to 0. So that's the output that we would see in the case of an example of classification. So that is the basic structure of a CNN, a convolutional neural network. And as you learn, so when you're first learning about CNNs for classification or any other tasks, you can improve your intuition about model design by doing several things. For example, you can change the number of convolutional layers and see what happens. This is just a specific here kind of arbitrary structure. You can choose different layers and so on. So you can change the number of convolutional layers. You can increase the size of your convolution kernels. So in a moment when we define the network, the convolutional layer is one of the parameters will be the convolution kernel. So how many filters, filtered versions of the image you would want. So that's something you can play around with, all these hyper parameters. And you can change also the loss and optimization functions to see how your model responds, change the learning rate. You can add other layers to prevent overfitting, change the batch size, and so on. So you can do that. There's a lot of hyperparameter tuning that you can do. So now that we have the basics, conceptually we know how CNNs work and how they're structured. How do we implement that in code? So let's go ahead and do that. And here, the first thing is we need some import. So we need to import torch. We also need to import torch.nn. Let's say as nn, and then import torch.nn.functional as f, and we can just go on to the next here. There's other things that you can do. For example, you can choose to, let's say you're going to initialize the weights in a specific way that you want. So instead of letting those weights initialize automatically by themselves, you can set to initialize in a certain way. So optionally, you can import torch init as I, and then you can, for example, sample from a normal distribution on weights and do that. And it's something you can play around with as well. So the first step here is we're going to create a class, and here we'll call it net. And then it's going to inherit from nn.module. So it's the base class for creating a neural network here. And the first thing, we need to define our init function here. We'll pass in self. This is just a pretty standard way of defining a class in PyTorch. The first thing is to call the base class or the super class here, our network, self, and then call the init function on it. So pretty standard. And then the first thing that we want to do is define our layer. So what kind of structure do we want for our network? Now, in this case, for this example and for the next few lessons, what will be the specific example that we'll be using to learn about a CNN is for facial key point detection. So we will learn to classify, to predict the facial key points, so locations on the faces of people on images. So detect where are the eyes, where's the mouth, the nose, the contours of the face, and so on. So we call it facial key point detection. So we're going to want to standardize our data so that it comes into the network in a specific format. So the format that we will pick will be a 224 by 224 image, and then we want it also to be one color channel, which means grayscale. We want to take in a grayscale image, which will make this simpler, and a 224 by 224 image. So that's a standard input that the network will always see. And in the next lesson, we'll go over preparing the data and how we prepare and transform the data so it's ready to be fed into our model. So we'll first go ahead and define our first convolutional layer. So we're gonna go and create our we'll call it conv1, and here we're going to use nn.conv2d. And this is from PyTorch. This is how you would define a convolutional layer in PyTorch, and this takes 3 parameters. So the first one is the input image channel. So because we're going to be dealing with a grayscale, which is one color channel, we just want 1. And then the next one is how many output channels. So how many feature maps do you want to output here from this layer? So in other words, how many convolution kernels, how many filters do you want to apply to this image? How many different versions of the filtered versions of the image do you want to output from this convolutional layer? So in this case, we'll start with 32. And you can play around with all of these values and see how it changed. And you can look at the literature and papers. So for facial key points, the structure that we'll look at is something that has been proven to show and work really well for facial key point detection. And now, what is the dimension of the convolution kernel that you want to use? So in this case, we'll use a 5x5 convolution kernel to scan our images. So this is our layer. Now, what is the output of this layer, the size of the output? Because the input for the next layer, and we're going to call it conv2, so the output is the size is going to depend on the output of this layer. So the output for this layer, you can get it for a simple formula, and I'll write it here. So the output size is equal to, so I'm just going to write the formula here. So, and then I'll explain what it means. Plus 1, and this will be equal, in this case, 224, our input. So here we're going to take in the width or height. So it's a square, so it doesn't matter. So 224 of our input, and then we're going to subtract the filter size of the convolutional kernel size, which is 5 here in this case. And then we're going to divide by the stride, which is just 1 here, just how much this window, these filters these convolution kernels are shifting as they scan through the image. So it's just 1. Let's leave it at that default value of 1. And then we just add 1 here. So this is just the formula of how to get the output here. And this is a tensor. So here actually, so the output tensor, just a PyTorch tensor, will have dimensions 32, 220, 220. Why 32? Because you're outputting 32 feature maps, 32 versions of this filtered image, and then this is the output size 220. We're still looking at a square image. It's standardized. It came in as 224, 224. So now this is the output. Now, after we apply so what we're going to do before feeding it into the next convolution layer is we want to apply a max pooling layer, right? We want to reduce the dimensionality of this input using the max pooling layer that we talked about. So the max pooling layer that we're going to use is going to decrease the dimensionality by half. So after one max pool layer, this becomes 32, 110, 110. So half of what it was before. So it's reducing the dimensionality, the size in half. So this will be the input for the next layer. So here for our next layer, the input will be 32. And then so here again you can play around with these filters, but for this next layer, how many filters do you want to output here? So how many feature maps, different versions? So in this case, we decided to, I decided for this structure because it worked well to do an exponential increase in the number of features. So by exponential, I mean a constant doubling rate. So we're just going to double it every time. So instead of 32, we're going to output now 64. And then the convolution kernel dimensions, now instead of a 5 by 5 matrix or matrices, we're going to do 4. So 4 by 4. And we're going to be applying this same formula. So, for the next layer. So the next layer we want a self.com3. So we'll do 4 layers for this network. And again, you can play around with that. Well, actually, yes. First of all, actually, we need to. Yep. Actually, first of all, yep. Conv 2D. Now you put in your your parameters 32, 64, and 4. Great. So the next layer, another conv2d, and remember we'll be applying max pooling, and you'll see once we create a forward function how that works. So this will take in now 64, output 128, and now we want 3. Again, this is just decreasing linearly here. And now the next self.com4, conv2d, and 128. And you can pause the video and see how this is working, but it's pretty consistent. 56 and then 2. So the convolution kernel dimension, those matrices are decreasing linearly, but the amount of feature maps that you're outputting is increasing exponentially, so doubling every time. And here we just pick 4 layers. So now let's go ahead and define our next layer, which is, or our max pooling layer. So here we're going to do let's just call it pool, and we're going to do nn.maxpool2d, and we want a 2 by just 2 by 2 for those parameters, because we want the dimensionality to decrease by half. This is how we achieve this decreasing by half, and this is actually pretty standard, and you can play around with those parameters as well. Now, there's another thing that we want to do before they're fully connected layers, which we didn't discuss it, but we'll discuss it now real quick, which is we want dropout layers. So we want, in between the layers, we want to add dropout layers, so to reduce our chance of overfitting. So there's a chance that some nodes in the network will get more attention, so to speak, that they will train more than others. So what we want is to introduce layers that turn off certain nodes in a given layer with a probability, and this will just make sure that they're all of the nodes in a given layer, all the neurons are trained, everything is trained consistently. So we're going to here create some dropout layers to help us with that, to prevent overfitting. So we'll go ahead and declare a dropout 1 and then dropout, and as you can see, they're all coming from NN here, from these are all PyTorch. And the parameter is the probability that you turn off a given neuron. So for this one, we'll do 0.1 probability, and we're going to define 6 of these dropout layers, and we're going to use them in between every single layer, essentially, in our network. And again, this was I learned through experimentation, hyperparameter tuning, and just testing what works. And for facial key point detection, adding these dropout layers in practice, experimentally verified that it works really well. So we're going to define some more layers, dropout, and the probability we're increasing it linearly here. So now we're going to do 0.2. Let me just make this a little faster here. So 3, 4, 5, and 6, or 6 dropout layers, and then we're increasing the probability that a neuron is turned off here linearly. So again, a lot of these things you can just test and try out and see what works. And this is by no means perfect. There's things other things that you can do, and to increase, let's say, how accurate is your model at the end. So we're going to have here, for this particular case, 256 outputs here from our last convolutional layer, times. So we're looking at the dimension for our first fully connected layer, 12 by 12, a filtered / pooled map size. So this is what we're going to get. And 12, why 12 by 12? If you actually keep doing this math here, this output size for this last one, you'll see that the output comes out to be 12 by 12. And sometimes if you ever get something like, for example, 55.5 here for the size, we want just integer values, so you would just round down. So you would just do 55 instead of 55.5, and that's what you would pick for your size. So let's go ahead and create our fully connected layers. In this case, we're going to pick 3 fully connected layers. And again, you can play around with this and see what works. So we're going to call it FC1. We're going to assign an n dot linear. It's just a linear function. It's going to take in our input. So it's 256 times 12 times 12. So that's our input. And then this is arbitrary, but let's say 1000. This happened to work well in this case. So for our layers, we're going to add another linear. Feel free to pause the video and check and see what's happening. And then we're going to add another layer. And you can pause and check if something's not clear, if you want to stop and pause and see and just see what's how everything is working. So here we want to output 136 outputs, because this will be a regression problem where we want the network to output a value of x and a value of y for the coordinates of a facial key point, or a point on a face. Let's say the point around the eye, the nose, the face. So you're going to output all of these different values, x and y coordinates, for 68 different key points. So 68 times 2 is 136. So we have an x and y coordinate for each one. And those will be the coordinates on the image where those key points are. Again, points around the eyes, the nose, the mouth, etc. So that's it. That's what we have for our init function. We have defined all of our layers. So now we want to define our forward function, which is the feed-forward behavior of our network. That's going to take in a PyTorch tensor, standard PyTorch tensor. And now here, so x is the input image, of course. And let's go ahead and now see how everything is going to be working now during training. So during training, this is what's going to happen. So you're going to have your input, and then the first thing is you're going to do. Okay, so I'm just going to do it real quick here and then show you what's happening. So in this particular layer here, you have your self.conv1, your first convolutional layer, and then you're passing in your image tensor here. And then to the output of that, you're applying a ReLU, which is coming out of this of torch and n functional, which is our ReLU activation function. And then to that, we're going to apply self.pull, so our pulling layer to that. So this is just a condensed way to put it together. And as we said, we want to put dropout layers in between. So to the output of our pulling layer here, we want to apply self.dropout1 and just pass in our tensor here. And the output here of our previous layer. So this is the basic structure. And to save time, let me just go ahead and copy them. So for the first one, we have the second layer, the second dropout, and so on. Again, feel free to pause the video and just make sure that everything makes sense. And we want also the last one, the fourth convolutional layer that we defined here. So now we have that. And now, before feeding our output here to the fully connected layers, we want to flatten our feature maps into a vector because it takes them in as a vector. So this is where we're going to do pretty standard here in PyTorch, how we flatten our vector here. So now that we have that, we're going to say f.ReLU. So we're going to apply our fully connected layer, pass in our tensor, our first fully connected layer, and then also apply our ReLU, an activation function to the output of the fully connected layer, before feeding it into the next layer. So we're going to use our next dropout layer, dropout, and then pass it in here. And let's go ahead and do it. Oh, this is actually dropout 5, yes, because 1, 2, 3, 4, 5. Then we do it again. We want our second fully connected layer, and we want our dropout 6 here. Let me actually leave some space so you can see more clearly what's going on. So now here at the very end, because this is a regression problem, for the final output, we just want to output the final layer. That's it. And that will give us our values for our key points. It's going to output 136 values corresponding to the x and y coordinates for each one of those key points, facial key points. And all we want to do at the end is just return that. So here's how we defined our class, our network, inheriting from nn.module. We define our convolutional layers, our pool layer, and it's the same pooling layer, but as you can see, we're using it at every step. Our dropout layers to prevent overfitting, just make sure that all of the neurons in the network are getting the same amount of training on average. Our fully connected layers to flatten to get our feature vector, and then our output, which will be our predictions. And then in the next lessons we'll cover how to prepare the data to be fed into this model, into this class, to get this PyTorch tensor, and then from there we'll go into training and evaluation, hyperparameter tuning, and so on. So thank you for your time, for learning about convolutional neural networks in PyTorch. And questions, thoughts, comment below. Contact me if you have any questions, anything, any way I can help you. And we'll see you next time.